Basically, we were almost done today. We saw what the purpose was, compare the means. I've showed you how to formalize the model and the assumptions for what we do and what do we do. Then we test hypotheses about the means to check whether there are any differences. That's how far we took it at this point, and then there were some computations to put in the ANOVA table to actually get to the point where we could do that. That was basically looking at the means in various ways. Then we need to finalize the story about what's going on. So in a way, we go back to the means again. And it's not rocket science, I hope you can follow. We start with the means. We do a bit of variability investigation to check whether signals are really signals or it's just noise, everything. And then we go back to the original means to sort of complete the story about what's going on. That's what the post-hoc analysis, exactly as last time. Now we have means for treatments and means for blocks if we want. So the way it's being put in the notes is that what we should do is to do justice for one way. So there are no specific method boxes for the two-way post-hoc part. But it doesn't mean you're not expected to be able to know how to do it, because you're told, go back and use the same boxes as you were given for the one-way with two minor tweaks to make it work for the two-way setting. Namely, of course you should, in the formulas, use the MSE. I mean, we also called it MSE in the one-way. And I mean, the problem could be that data that really is two-way data, you could miss the point that they were two-way and analyze them as if they were only one-way. That's possible, right? You could just forget about taking the blocks into account. And maybe, in fact, I was a bit rapid at that detail, but let me then jump back just to emphasize it was so simple that I forgot to say it, but please note the simplicity in how to make it happen compared to what you already knew. Namely, instead of just writing y tilde treatment, that's what we did last time. Y as a function of treatment groups. Now we write y tilde treatment plus blocks. Exactly like we moved from one to multiple regression. It's straightforward. So I just wanted to emphasize that. So we use the MSE from the two-way computation, and then instead of using n minus k degrees of freedom as we did last week, we use these degrees of freedom. With those in place, we use the same method box as last week. That's how to do it. And you can do it with either treatments or with blocks. You can do it one way or the other way. It works either way. And then we have this, and that's all of this now is repeat, so take it as a repeat. Everything these two did last time and today is very much copies of each other with this little extra two-way thing on top of it for the stuff we do today. If we do single pre-planned comparisons, this is this little thing about whether I compare. Like if I were a company, maybe I have two prototypes already. I know I'm gonna choose one of those two prototypes. Then I put in a number of other products to compare, maybe competitors' products, whatever, other prototypes. But I know at the end of the day, when I've done this study, I want to choose between those two prototypes. For some reason, that's where I am. Then that's what I mean by a pre-planned comparison. Then we can go ahead and do something which is very much like the two-sample t-test, independent or paired anyway, but still not exactly that. Do we teach music here also? Well, sounds interesting. I should do some more. Yeah, my music has gone today, but anyway. We take the pre-planned comparison. We take the statistical uncertainty of that comparison, which is something that looks very close to something you've seen before. It's the, you could also call it like this, it's also MSE times Ni. And then these Ni and Nj actually in this today they are the same. In the two-way ANOVA, these are the same. In the one-way box, they could be different. But I mean that they could be different, that's not a problem, because when we have a full two-way table, it's the same Ni and Nj always, right? So, but it doesn't make the formula wrong to use. It's exactly similar formula to what we've seen before. And we just need to use the right degree of freedom to find confidence intervals like that. And we could do hypothesis testing similarly. Question? Shouldn't we use... good point. Thank you. You're right. So this is apparently a direct copy of the formula from from the one-way thing, right? And you're completely right. For this to make sense here, this should be, good observation, I missed that, should be k minus 1 times L minus 1. Maybe the original idea was to show the formula from back then and not the real thing. But anyway, the way I put words on that, we should have that in place also. Thank you. So same formula, but using these two differences up here, right? And then a little thing on this pre-planned thing again, and the Bonferroni, it's almost going away in the bottom here. If we do not only do a single or maybe two pre-planned comparisons, if we just do all pairwise comparisons between a number of treatments, if it's a kind of screening investigation we're doing and we want to talk about significant differences between all possible pairs of these products that we're testing, if we're in a product testing mindset here, it could also be treatments, medical treatments, it could be basically anything that we compare, where we want to compare means. Please get them. I mean, there is a limit to how many different examples I can find the time to put into my talk here, and you're many different people, but I hope you get the point that the idea of comparing more than two means with each other is a pretty generic idea that could come up within any kind of engineering area that you're working with, and in any kind of other area. That's why students in all sorts of areas are being taught exactly similar tools, because it's relevant for economists, it's relevant for you name it. Back to this, if we want to compare all of them, we should not get too enthusiastic with a few p-values or that is a few confidence intervals giving some interesting messages. We should protect ourselves for this selection that we do, and just looking at 100 p-values. Of course, some of them will be small, right? 100 p-values, there will be 5 below 5% if nothing is going on, and we shouldn't get carried away about seeing 5 below 5%. We should be more strict on how we would evaluate and quantify uncertainty in such a case. There are many ways to do this multiplicity correction, as some would call it. Very nice, not the best, but for terms of simplicity and generality, that's my personal favorite to introduce in a class like this, is the Bonferroni way of approaching this problem, because it's a very generic thing and similar challenges could come up in many other selection situations. The idea is, if I have 10 products, let's say 12 products, like the TV data set. That was actually 12 products in the outset. If I make all pairwise comparisons, that's 12 by 11 divided by 2 actually. It's a diagonal, 12 by 12 or matrix, but then it's everything above the diagonal. If you count that, it's 12 by 11 divided by 2. That's 66 comparisons. Then the Bonferroni rule would be, if that's the name of the game, if that's the game I'm doing, then don't use 5%. That's much too optimistic when you just do 66 hypothesis tests by one press on a button. then I should use 5% divided by 66. Much more critical, right? Much more strict level. I would require differences to be more different to allow myself to call them significant. And that makes sense, right? Because, of course, if I take 12 products, the difference between the smallest and the largest in 12 random means tend to be larger than just the difference between two specific. There are many different ways of talking about this multiplicity issue or selection problem. So that's why we need to deal with this or talk about this and this. It's a bit difficult thing, especially when we do exam and exercises in a class like this, because what is pre-planned, you don't know, because you just get the exercise and the problem presented. So we have to put it into words, but it's a very important ethical thing when you're there yourself and plan the studies and you make the distinction. It doesn't really work by you just if you investigate 1,000 genes and then one of them at random gets a signal. Whoa, that's my gene for this or my gene for that. That's not enough. You need to protect yourself that you actually looked at 100 genes to pick out the single one that gives a signal. That's another place where those protections against multiplicity is important and is being used also. Yeah, I was a bit ahead of myself. We can do confidence intervals and we can do hypothesis tests. We've seen it before. They are analogies of each other. And here I put it in a version, so I didn't put the degrees of freedom, so they are the right choice of degrees of freedom in this formula, of course. And the same thing goes for the multiplicity. Let's see how we are doing. There you go. Slightly tricky. Seen it before, but I changed some things. Gotcha. We talked about this plot a number of times. I shared a paper with you from Nature Method, which does not at all touch on the issue that I'm pushing you with here. Actually, but now you're on. You learned about two-way now. So you're beyond what your people are talking about in this Nature paper. We talked about it back with two independent samples, first time. The plot is from that part of the book, right, where we talk about two independent samples. It's the same plot that you've seen a number of times. When it's two independent samples, that is this paper I shared with you, and funny enough, people are discussing error bars in Nature. These are things that you're taught in this basic stats class. Why the heck? I mean, people don't discuss Newton's law in Nature anymore, right? Newton's law, we pretty much agree on that one. It hits the floor. It's a parabola. No one discusses that in Nature. Why the heck do they discuss as simple an issue when it comes to looking at errors? Isn't that odd? Having taught people, wise people like you for 25 years, I find it a little bit odd. They could have asked me 50 years ago. 30 years ago. I could have answered it. It's just a very interesting and pretty intriguing thing that people tend to struggle with uncertainties in life. So you can really make a difference out there if you learn to handle them. Because apparently, uncertainties is a difficult concept for people to handle. People still discuss what you are taught in this class in Nature. Isn't that amazing? So listen in. and you're on top of the world. Back to the point here. We had this square root 2 thing, which was the original purpose of this plot, to make the point that they're not really it's not really correct to study whether they overlap or not. And then originally we had this point of saying if they don't overlap, of course they are different, right? And then if they more or less slightly overlap, probably they are different. That was an okay answer a few weeks ago. But when it's a paired design, and that is an example of a blocked design, a paired setting is a block design with only 2 treatment groups, right? So paired data are examples of blocked data as we are talking about today. And I mentioned this in my box plot talking in the beginning. The point is, I don't know anything about the error variability by looking at these means and those confidence intervals, because I have not taken out the block variability in such a plot. This has also been studied by people that study statistical cognition, experimental psychologists. Quite recently, you can find scientific papers testing, and you're just to make you feel, I don't know if you feel comfortable about that. I mean, wise people tested, researchers tested in a similar plot. They'd flunked exactly the same as you did. Jumped in with both legs and answered exactly like you did. Similarly wrong. We don't know when it's a paired design. It's the individual variability is part of the picture. So they're not even comparable. It's not a picture that can answer that question in any way. Good.